Hello and welcome to another problem solving session. And as you can see here, there is a problem at your screen, and it simply says that there is a small ball of mass m, as you can see it here, and a thin uniform rod of length L and mass m lies on a smooth horizontal surface. The ball is given a velocity v in the horizontal direction perpendicular to the rod. You can see the figure. The ball collides with the rod elastically. That means it's a case of an elastic collision at point B at a distance L from its center. Center is at point O. And determine this distance, that means L, in three cases. The first case is immediately after the collision, the ball stops. Okay, fine. Second case is the ball transfers maximum momentum to the rod. And the third situation is the speed of the end of the rod after the collision is equal to 0. So there are many things visible here. In the absence of any external forces in the plane of motion during the collision, the conservation of linear momentum is applicable for the ball plus rod system. And to find the angular velocity of the rod, the conservation of angular momentum is applicable. And we can also visualize the rod as spinning around an axis, passing through its translating center of mass. Since the linear velocities of ball and rod changes after the collision, and an angular velocity is also imparted to the rod, we can have three unknowns in general. Since the collision is elastic, so we can have the conservation of kinetic energy at our disposal in case we need them. Since I think we find all the principles that can be applied to solve this problem. So let's plan the solution of the problem now. And of course, we would like to solve the problem relative to the laboratory inertial frame of reference that is attached with the ground. And well, we have as earlier we were talking about, since the collision of the ball and the rod is elastic, and the system of bodies, that is rod plus ball, is not affected by external forces along the horizontal surface, we are going to use all three conservation laws: the law of conservation of momentum, linear momentum, the law of conservation of angular momentum, and you can say law of conservation of kinetic energy, since the collision is elastic. And you can see we have chosen the coordinate system as shown in the figure. You can see their x and y axis, and origin is of course placed at the center of the rod, and the axis of rotation you can see here. It is also passing through the center of the rod, perpendicular to the horizontal surface, and directed from the plane, perpendicular to the plane of the drawing. So let's write down these conservation principles for the selected system of bodies for the time interval before the collision and immediately after the collision. And the conservation of momentum, I would like to this conservation law of its projection on the x-axis. And so I would like to write here something like mv equals mv dash plus mv double dash. Here v is the velocity of the ball before the collision, and rod was at rest. That completes our the total linear momentum before collision. And then I assumed that v dash becomes the velocity of the ball after collision, and v double dash is the velocity of center of mass of the rod after collision. Now I'm going to write the law of conservation of angular momentum relative to the selected axis, and you can see here you can write mvl as the initial angular momentum, and this was the moment of momentum or angular momentum before the collision. Rod was initially at rest, and then we can write the angular momentum of the ball itself about the same selected axis as mv dash l, v dash being the velocity of the ball after the collision. And the angular momentum due to the translation of the rod about the axis passing through its center of mass will be equal to 0. So since we have selected a particular axis, so we will get only a spin angular momentum of the rod about this axis, and we are going to write its moment of inertia about the selected axis multiplied by angular velocity it just obtained. And so this completes our equation of conservation of angular momentum relative to the selected axis. I'm talking about this axis passing through this point. And now we are going to write down the equation for conservation of kinetic energy. Initially it was simply half mv square, or finally after the collision it becomes half mv dash square plus half mv double dash square plus half I omega square. And this is our equation number 3. And in case you can write here that I naught is definitely here the moment of inertia of the rod about an axis passing through its center of mass is and perpendicular to it will be ml square by 12, L being the length of the rod as stated in the problem. And we would like to write one more equation, and that is the velocity of point A. And so to write the velocity of point A is here. You can see here is the point A, this one. And we are going to use the principle of superposition of velocities, that is also known as relative velocity concept. So you can see here we can easily write the velocity of point A equal to velocity of center of the rod, and minus omega L by 2. And you can see the picture here. Why I am writing like this. Omega is this, so this is the velocity of center of the rod after the collision, and with respect to its velocity being omega L by 2. So I wrote the equation of velocity of point A, and you need to solve each one of them, and if you wish you can find those different quantities like v dash, B double dash and omega you can get, and also you can get V and put the relevant information that is the part of the problem, and you can get your results easily. So there is nothing more to do, and we solve this problem and you can do the rest of your job. Thank you very much for watching.